So, good afternoon, dear Portugal and dear listeners. I'm very happy to be with you here today with you to talk about science and fiction and specifically space. So, I will now try and share my screen. And I hope you can see it. Now, before I go on, we're going to try and have this as a bit of an informal discussion today. So Joana Enriquez from MAT is here with us this afternoon. If you have any questions, she may interrupt me during the presentation to ask these questions, so we can try and be a bit interactive despite Corona times and try and make it so as if we were together. I really love space, and I'm very happy that I'm with you this afternoon, and I'll try and share a bit of insights on what we do and why we space people also are, very passionate about what we do, because we believe it's for science, it's for economy, and it's for the environment. And I'm very happy if you decide to challenge me this afternoon, or otherwise feel free also to contact me afterwards. So I come from the European Space Agency, and the European Space Agency is an international intergovernmental organization which is made of 22 member states. 19 member states are of the European Union, as well as Norway, Switzerland, and the UK. We also have a number of associated states, Slovenia and Latvia, as well as cooperating states, and we have agreements across Europe with other member states of the EU. You can see the flags at the bottom, and hopefully you already spotted Portugal. Indeed, if you didn't know, Portugal founded its own space agency in March of 2019 called Portugal Space, and Portugal Space has been very, very active to try and build up and implement the vision that the government had issued a year earlier in 2018, also called Portugal Space 2030. And this vision, what does it say? It says that Portugal wants to become, by 2030, a recognized global authority in space, climate, ocean interactions for social economic benefit. If you actually read this document, it's wonderful. It has lots of interesting elements of what Portugal believes that space can contribute. But what I find there's a specific sentence also in this vision which says that Portugal wants to do this in a European context and for the benefit of the entire humanity. And I think these are perhaps the most beautiful words in the whole document. But in any case, feel free to read it, and do contact the agency to get more information about what Portugal is also doing in space. Portugal Space is the representative to the European Space Agency on behalf of Portugal. One of the aims that Portugal has in space is to multiply the space sector in Portugal by a factor of 10 and create about 1,000 skilled jobs by the end of the decade, and to have an overall investment of 2.5 billion in these 10 years. And this is supposed to be a combination of public and private investments. Now, hopefully in the course of my talk today, you'll see how this comes to be, right? So the 1,000 skilled jobs are 1,000 skilled jobs associated to space and bringing benefit to other sectors, right? In fact, we believe, those of us working in space and hopefully those benefiting, believe that space is an infrastructure, just like trains, just like buses, just like any other infrastructure that we have, telephones, et cetera, and it's an enabler, meaning that the sector itself is important as an industrial sector, but it brings benefit to other sectors. And in fact, that's what we try and do. We want to bring benefit to society. We want to bring benefit and grow the economy. And we believe that space can contribute to taking care of the environment. And by the environment, we don't just mean also the environment here on Earth, taking care of this wonderful blue dot, which is our very own spaceship in the universe, but also taking care of what we do in space is sustainable. And I'll be sharing a couple of things and also a couple of examples where Portugal is doing great things. For those of you that are interested in economic growth and want to hear some numbers, I have a picture here from 2018. Actually, it shows the global space economy in dollars, and what you see in the middle is $360 billion. It's a sector, it's growing, And when you look at the picture, you see that there's different elements to it. So there's the actual satellite manufacturing here in gray. There's the launch industry, which are smaller parts. So this is where the hardware happens together with ground equipment. So it's the in-space elements and the in-ground, on-ground elements. And these contribute to a larger economy, which is also based on satellite services. So everything which takes space-based data, be it Earth observation, be it telecommunications, be it Galileo, so positioning, navigation, and timing, um, and take this and brings some added benefit to other sectors. And you see already here in the table, agricultural, change detection, disaster mitigation, meteorology, and we'll look at some concrete examples as we move forward. So my message again here is that whereas we invest in an infrastructure, the investment part is relatively small compared to everything that we can do with this. And this picture is small compared to where I believe and space people believe the space economy can grow and how we can even more impact and bring benefit again to society and economy. At the European Space Agency, but this is something that is shared among other agencies, therefore also national space agencies, hence also Portugal Space, is that an agency can play multiple roles in space. Space is a sector, an economic sector, which is still growing. It hasn't completely unfolded the capability of everything that it can do. And therefore, the public sector side has to play different roles to make sure that it continues growing and can bring that benefit and maximize the benefit that it can bring. So we act, for example, as an R&D entity where we look into new hardware technologies. The picture that you see here is Aeolus, which is an Earth observation satellite, which now measures the 3D wind profiles across the atmosphere. And I'll talk about it in a second a little bit more. Sometimes we partner with industry and public-private partnerships where we believe and industry believes that perhaps the market segment is there, or the industry has a mature idea. There we partner. Sometimes we try and just be customers. So where we really feel that the market is developed, we play, if you will, anchor tenancy. And anchor tenancy is a very important concept for the success of any economic sector. Sometimes we are enablers. So we have infrastructure that the agencies own, and this infrastructure is put at the service of, for example, small and medium-sized enterprises, small companies that otherwise would not be able to own this infrastructure, and they can use it and therefore develop a product which they can then sell on the market. And sometimes we are just brokers, meaning that we put, for example, space in products together with non-space sectors, and by that, relationships and network starts up, and a market can also develop. We do this through industrial policy, and I won't read all of this, but as I said, when space started off and when we started looking into how we can develop this sector, it was important to grow industry, grow champions that would produce the hardware and produce the service and applications that are now used across the world. And in order to do that, you need to have an industrial policy or an innovation policy. And this has been especially also important for Portugal. And you see here just an excerpt, so it's not exhaustive, of some companies that are very, very successful in space and Portugal, and with whom we will perhaps continue to grow the benefit that space can bring to the entire economy and to society. When you look at the logos, you will see that there's a bit of everything. There's software companies, there's hardware companies, there are entities which aren't classically spaced. For example, there's also ammonium cork composites. They produce isolant material for launchers. For example, right? That was just one example. And many of these companies have very exciting elements that they produce and contribute to space. So if you're curious to know what Portugal does, you can also have a look again, either on the website or on the websites of these individual companies to discover what they do. Through space activities, as I said, we space in people believe that we can help tackle climate change, address migration, mobility, all of these global challenges, including, addressing the simple fact that humanity is curious and that scientific enhancement is important to make sure that we are a successful and wise species on this planet. What we also do is that we look at the sustainable development goals and see how our elements, so the information that we can bring, the data that we gather, can contribute to addressing these sustainable development goals, from no poverty to a life below water, which is something which is especially important to Portugal, given the responsibility it has for the Atlantic. If you want to find out more, you can either go again to the Portugal Space website, where they give, and I have a screenshot here, examples of the Sustainable Development Goals and some examples of how space contributes. We also have at ESA a space catalog for these Sustainable Development Goals. So feel free to explore. I was in preparation of this talk, I was actually looking into these myself, and I ended up spending an hour finding out and looking at new examples, which were very great. At ESA, and then we do activities in a number of different areas, and we call these programmatic pillars. These are science and exploration, safety and security, applications, and enabling and support. So in science and exploration, we look into the secrets of the universe, of our solar system. We bring probes to planets, and we go down into their atmospheres. In exploration, of course, we have contributions to the International Space Station. We prepare for human exploration forward to the moon and onto Mars. We do research, fundamental research, and I'll be talking about that in a second, into human physiology. In safety and security, we look at safety and security aspects both in space as well as from space, and I'll talk about that as well. In applications, we have Earth observation, telecommunications, and navigations, and these are the ones that admittedly most contribute to bringing downstream services to, for example, other sectors. And again, there I have some examples for you. In enabling and support, we develop technologies, and we have our own fleet of launchers, again, of course, developed with our member states. And we're looking also to develop micro launchers with our member states, possibly in public-private partnerships, because we believe that there we can see a development of a commercial market. And then we also operate satellites, both for ourselves, so for example, our scientific assets and missions, but also for our partners. We have strong partnership with European Union, which hopefully will only get stronger over the years. In Europe, we have very many institutional players. Sometimes it feels like we're not working enough with one another, and I can only hope that as we move forward, the institutional side will work more and more together, because space can really bring benefits, again, to society and economy. So what I'll do is I'll take you through each one of these pillars, and I have various slides explaining things which I personally find fascinating. My background actually is liquid rocket propulsion, so I start with launchers. I don't know if you've ever wondered why these launchers are so big. They're really huge. For example, this is the Ariane 5G Plus. It's a version of the Ariane 5 that doesn't fly anymore. It was used for bringing, for example, Rosetta, if you've heard of that mission, to a comet. It was used to launch Rosetta. Ariane 5 G Plus was 730 tons heavy, and it was 46 meters high. So it's pretty big. It's considered a 2.5 staged vehicle, and I'll explain to you in a second why. It has two solid boosters with, and you see there it says the acronym is P241. If you ever come across such elements, then you know that P stands for poudre in French, meaning it's solid, it's a powder, and 241 actually means the loading. So it means it has 241 tons of solid propellant on board. It's quite a beast. There is one main cryogenic stage, as you see here, and the acronym says H170. H means it's cryogenic and it specifically uses hydrogen, liquid hydrogen, and it has 170 tons of propellant on board. And then there is one hypergolic stage. Hypergolic means that there's propellants which are storable at room temperature and they start burning when they come into contact with one another. That means that they're very reliable and it's easy to ignite them. So we don't have to worry about them actually, the stage igniting. So it gives us some more reliability. Now, if you look at the relationship between the weight of the Ariane 5 and the payload, in this case of Rosetta, you see that it's below 1%. And in fact, a lot of what these rockets do is they have to provide a lot of force to bring these payloads into orbit. And now, if you imagine that you had, for example, a nice box on the floor with a present inside and you had to lift this box, if the box is just a very thin cardboard, the force or the effort that you make in lifting the box with the present inside is related just really to the present, because the present will be the heaviest thing in the box. If now you imagine that the box is made of very thick wood, the present is only a very small part of what you are lifting, and so your effort will be even larger. And what I'm trying to tell you is that when we build these things, we're actually interested in bringing a payload into orbit. And it takes a lot of energy to bring things from the surface of the Earth into orbit. And therefore, we try and build structures which are as light as possible. Unfortunately, we cannot build it out of paper because it wouldn't resist. But we try and build them as light as possible in order to optimize the payload mass that we actually bring into orbit. If I look at the next generation of launchers that we will have an Ariane 6 and a VEGA-C. And what you see here again are solid boosters and cryogenic stages. Again, cryogenic meaning that they have very cold propellants on board, which are liquid at very deep -Celsius temperatures. And I'll show you in a second how much. And what you see here as well is that we have, for example, the solid booster, which is here 120 C plus. Is a common solid booster between the Ariane 6 and the VEGA-C. So we're also trying to build modular to, if you will, it's like a Lego building blocks, right? The more commonalities we can have, the closer we also come to reproducibility and being able to reduce costs of single elements of these launchers. I'm sure that those of you that have been following space activities have certainly heard of SpaceX and the Falcon 9 rocket, which is a very beautiful rocket. It's fundamentally different to Ariane 5, and this is something that people don't necessarily know if they don't, take time to look into it. The Falcon 9 is completely based on liquid rocket propulsion elements, so there are no solids on board. It uses, instead of hydrogen, it uses kerosene, and it's actually built, unlike Ariane 5, which is built to reach geostationary orbit, which is at 36,000 kilometers from the surface of the Earth. Falcon 9 is optimized for reaching 200, 300 kilometers altitude. So that's why it's also different. And what you see here is that it has a large number of engines at the bottom, not just one that Ariane 5 has, which is the Vulcan 2. You have here 9 Merlin engines. Okay, so it's a fundamentally different rocket for a different purpose, but of course these rockets are in competition. And for those of you again who are interested in the economics of what we do, we then have to look at the internal markets available to these rockets. And I have to say, in Europe, we don't necessarily build as many satellites as US does, and therefore it's true that our Ariane 5 is slightly more expensive because it has a lesser number of customers on which we have to finance the entire infrastructure and the industry. The fun fact or interesting fact is that the biggest customer for space launchers, so space rockets, is not NASA in the US. It's actually the MOD, so the Ministry of Defense. It's the Air Force with their spy satellites and such. So this gives you a bit of understanding on how also when we do space in Europe, our economic models are fundamentally different to the US. So it's difficult and I wouldn't say dangerous, but it's not informative to compare them just at a very superficial level. Just one equation for the presentation, and is the rocket equation. What the rocket equation does is it explains how much propellant mass you have to have on board a rocket in order to give the rocket and the payload on it the speed that it needs to remain and be in a certain orbit, right? So it's basically, you need to have a certain energy to be in orbit. Otherwise, if you're too slow, you fall back on to the surface of the Earth. And this the rocket does by expelling propellant at a certain velocity. Now, I was mentioning to you the present and lifting a present. And if you look back to what I was saying to you also about Ariane 5, it is a 2.5 stage rocket. And where does this staging come from? This staging comes exactly from the principle that if you have to lift something into orbit, the structure that contains the propellant, once the propellant is not longer in there, it doesn't fulfill the function anymore. So what you try and do is you optimize, you try and reduce the amount of structure that you have on board so that you can maximize the payload and the propellant that will bring that payload up. So the concept of staging is what gives rockets their fundamental look. And this is also why sometimes when we see nice science fiction films, we still don't have a single stage to orbit, not just one structure like an airplane that can get you from the surface of the Earth to orbit. Because today, the materials that we have are not lightweight enough to allow us to have the strength that we need for a structure that will get a single vehicle into orbit. This is the launch trajectory of Ariane, and what you see here is exactly what I was trying to explain. You see a liftoff. You see that the launcher does a little, goes up vertically and then sort of tips off at an angle. You see that the boosters are jettisoned, and this is exactly why. The boosters have burnt their 241 tons of propellant. They are just empty structure, and they get thrown aside so that the rest of the vehicle and the force which the propulsion system on the rest of the vehicle gives is not wasted on structure which is no longer interesting. Outside of the atmosphere, we jettison the so-called fairing. The fairing protects the payload. Once we're out of the atmosphere, we don't have the atmosphere putting pressure on the payload, and therefore we don't have to protect it anymore. So we can jettison that, and at some point we have separation of the stages. The main central cryogenic stage then falls back. Parts of it break up in the atmosphere, and the rest continues into orbit. There's payload separation, and then we also re-enter with the upper stage so that we can keep our orbits clean. If you look here at the bottom right corner, you will see that all of this happens in 1,400 seconds. So it's fairly quick. Now, just again, one final technical detail in terms of rockets that I'd like to share with you. If you look at the video, you see now the Ariane 5 going up, and what you see is the plumes of the solid boosters. And now you see that they're sort of changing color. They're not completely symmetric, and at some point they're jettisoned, okay? I don't know if you've ever asked yourself why, for example, they're still jettisoned when they're still burning. In a way, it's a waste. And if you were to cut these solid boosters and have a look what's inside, you would see that you have a grain, which is inside the casing, and this grain is placed with different possible shapes. And what this happens is that you have combustion along the surface of the propellant grain. So for example, in this picture, you would have combustion on the surface of the inner circle. And as the propellant burns, this inner circle surface area becomes larger and larger. And indeed, as it becomes larger and larger, you burn more and more, and hence the force that you produce becomes more and more. But at some point, you reach the end. And at that point, what you see is that the force drops very, very suddenly. Now, we manufacture these. They're not 100% identical. And so it can be that this decrease in pressure is not perfectly the same in two boosters. And if you have two boosters on each side of a rocket, and you have unsymmetries in this descending flank, what can happen is that the rocket becomes more difficult to control because you have forces which are more side forces rather than vertical forces. And this is why boosters are jettisoned before they end burning, and there is a so-called hot separation of the stages. One final element when we look at the Ariane 5, if we look at the main central stage and we look inside at a cut through, you will see that there's liquid hydrogen and there's liquid oxygen on the top. So it's two tanks which are separated, and each one contains the propellant needed. The Vulcan engine at the bottom burns 320 kilograms per second of liquid oxygen and liquid hydrogen. So it's quite a lot. And the structure is this big. Why? Because of course we have a lot of liquid hydrogen on board with us. It's 353 cubic meters, and liquid oxygen we have 130 cubic meters. But it's this big because the density of liquid hydrogen is very low. If you compare and look at the densities of the different propellants, you will see that the density of liquid oxygen, which is right up here, is about the same as water, right? So if we had 1 kilogram of water, it would be 1 liter. 1 kilogram of liquid oxygen is actually a little less than a liter, but it would sort of fit in a liter bottle. Liquid hydrogen, which is liquid at 20 Kelvin, which is minus 250 degrees Celsius, actually takes up 14 liters when it's liquids. So what you see here is, of course, these, I started saying, have you ever wondered why they're so big? Well, this is part of the reason why they're so big. Now, why actually do we use liquid hydrogen? Liquid hydrogen is very clean. When we burn liquid oxygen with liquid hydrogen, we produce water. There's hardly anything which is cleaner, really. And this is why some companies have looked into taking this technology and bringing it, if you will, back to Earth, and have built hydrogen cars. And what you see here is a range of companies that have developed sub-elements. One here, for example, at the bottom right-hand corner, Hype is a taxi company in Paris, in France, which has taxis which have fuel cells, whereby through electrolysis we have production of electricity by using hydrogen, which is then again brought together with oxygen, which is fed in through the air system of a car. We produce electricity, which then drives the car, right? So it's not electromobility through batteries, it's, if you will, electromobility through hydrogen and fuel cells. So that's one concept where we have seen that these technologies can be brought back to Earth for contributing to a clean environment. There are, however, also elements which, for example, burn hydrogen just as in a combustion engine. But I understand that there's a question?
Yes, Chiara.
Yeah.
Can
yes,
you hear
Joanna,
me?
tell me. Yes, I can hear
Okay,
you.
so
Tell
we
me.
have someone anonymous asking, being an ESA, Europeans gateway to space, and having in mind the European sustainability goals, what is ESA's position on space waste? What are the guidelines to treat its mission related to waste?
Yeah, so I'm going to touch that topic in a second. I have some slides to deal with that, but we are getting more and more stringent in what concerns debris. And, you know, if I tell you the honest truth of how this story goes, you will probably not be so happy, just as I was not. The European Space Agency, as such, brings elements to space, and of course, through that we have produced in the past debris. And there was a time where no one really was taking care of it. Now, the most elements of debris in orbit are actually produced or have been produced by the US, by Russia, and actually other countries beyond Europe. So when we were trying to move forward on this element back several years, it was always a question of why should we clean up space waste that someone else has produced, right? Where is the economy of it, because we invest, we want to bring that space debris down to keep it clean, but we didn't actually cause it, so why should we pay for it? It's not a wonderful message to pass, and it's certainly not a message I'm sure we would pass to younger generations, but from an economic point of view, I can understand that. Now, over the years, we have at the European Space Agency, together with those member states that really believe in tackling debris, and Portugal is one of them, I can assure you, we have continued to try and tackle it. And for the first time at Space 19 Plus, which was the ESA ministerial meeting that takes place where ministers come together to decide what ESA should do and Europe should do in space, there was a mission that was approved called Adrios, where Portugal has plays a significant role. And through Adrios, we will actually be taking down for the first time a debris in orbit. But that's only part of the picture, right? So taking down debris is part of it. We have to try and avoid producing further debris, and we have to consider things like in-orbit manufacturing and recycling. And there's a company, but I actually should keep that for later. So please wait, because I actually have a video to show you about Portuguese contribution to that topic. So if there's no further questions, I'll continue. What I wanted to say finally is that for those of you who have not heard yet, Portugal being interested in access to space because it contributes to the so-called democratization of space, so bringing space to everyone, again, for the benefit of society and economy, you'll hear me say that a lot, has been considering how to contribute to this and if it can be a business. And launching from the Azores is a possibility. And I have sort of a zoom out picture of the planet where it shows that the Azores, being in the middle of the Atlantic, being far away from land, are an attractive position because if you launch from there, the things that if something comes back down, it will go onto the ocean. So there is no danger, if you will, for humanity. Of course, we would then recover elements so that we wouldn't, pollute the oceans. But this is to say that Portugal is really interested in is looking at launching from the Azores with micro launchers. The regional government of the Azores, together with the national government, had put forward a competitive process to see if companies are interested. A number of companies have said yes, and I understand we're in the final process of this competition to see who could build a spaceport in Santa Maria. So perhaps one day you'll be able to see launches from the Azores. That would be great. I'll come and see them myself if that's the case. So I would now move on to science and exploration. Science and exploration sometimes are the harder elements, for us as space people to justify, because sometimes we are asked also by politicians, what's the benefit? Why do you do it? What is the benefit that we bring again to society and economy? And, part of me always thinks it's true. We have to explain what the benefits are. And part of me says scientific knowledge is a benefit for itself. And I find it difficult to put a price on scientific knowledge. It's the basis of human being. This is why we've become the way we are, because we've been curious and we've been looking into things and we've been evolving with the knowledge that we have. So it's hard to put a price tag on it. And of course, in exploration, again, it's the element of curiosity. If you're in the US, it's actually very easy to say, let's do exploration. The US spirit of pioneering is still very strong based on the history that they have. In Europe, we haven't, with the ones that remained weren't the pioneers that went to the US. So it's harder perhaps to justify. I have a complex picture here, which is a pyramid, which shows everything that we've managed to do based on scientific discovery. So what you see at the bottom of this pyramid are the various elements going from classical physics, looking into the smaller and smaller dimensions, from the atoms to the nuclei onto quarks, and who knows what's beyond, to the macro dimension, looking at planets up to stars, galaxies in the universe. And all of the scientific advancement and the big questions that we've asked ourselves and the answers that we've gotten brought us some technology that you see in red in this picture that we use today and is part of our daily life. This doesn't happen immediately. The time span can be anything from 50 to 100 years. But again, if point of just scientific knowledge being important is not enough. If you don't believe that statement, look at this pyramid, and I think you'll agree with me that we have certainly reaped on scientific advancement and research, and we should continue to do so. Now, in terms of space, we have a number of missions that we've developed, a number of space infrastructure that we've developed to look at different aspects of the solar system and of the universe. And what you see here is a picture of the so-called cosmic observers that the European Space Agency with its member states has developed. And I've put some Portuguese flags on just some. I'm sure I've missed others where Portugal played a contribution. We have anything from exoplanet research to looking into gravitational waves, which was LISA Pathfinder. And we also have a number of solar system explorers where we, again, look into the secrets of the solar system, trying to understand, why are the planets the way they are? Why they're so different? Did you know, for example, that Mercury has a magnetic field and it's not that much bigger than the moon? So why doesn't the moon, for example, have a magnetic field? And again, here you see that Portugal has contributed to a number of these probes. I'm sure I may have missed some others as well that have looked again into the secrets of the solar system and where we've learned things. Two exciting missions coming up are Athena and LISA. The one will look at hot gas structures and supermassive black holes. There's something called dark energy and dark matter, which is out there and helps us has helped us make models of why the universe is expanding and behaving the way it is. And there's some people that believe that dark matter and dark energy is associated with black holes, and we'll see that perhaps over the next years develop, and who knows, maybe there will be a Nobel Prize winner out of that research as well. Gravitational waves is something that was discovered some years ago, and we're going to send out a mission into space because things that you can't see and like dark energy, if it does have sort of a mass associated with it, when it when it accelerates, it causes a gravitational wave. So gravitational wave will be able to also help us detect those things that we can't see in the spectrum in which we normally observe the universe and the bodies in it. Through all of this that we've done in the past, we've also realized that the elements that we have on Earth and that can be found also perhaps in other parts on other planets come from the evolution of the universe. And just helium and hydrogen came from the Big Bang. Everything else sort of came from the stars, the various types and different types of stars merging, dying, exploding. And some elements have even been, as you see in the plot, sort of enabled through cosmic ray fission. So we've actually been very lucky, and everything that's around us has made all the things that we live on a day-to-day basis possible. One of the big questions that we've asked ourselves in the past is, where does water come from, right? For us to have life, we need to have water, but so the water didn't originate on Earth. This is what we understand today. So where did it come from? We built a mission called Rosetta, which had a small probe called Philae, a small lander, to go to a comet called Chury in shortened nickname language. And the idea of this was try and see whether the water that's on this comet is the same, could possibly be the water that's on Earth. So not exactly that one, but if the water that's on comets if the comets brought water to the Earth. So we built this mission. It took 10 years to get to the comet. We got there, and then we found out that it wasn't. But why? When you look at hydrogen, the hydrogen as such, as an atom, has one proton and one electron. But there's also sort of other variations of it where within the nucleus you also have a neutron. So you have a proton and a neutron and an electron. The charge remains neutral still, but it's heavier. Okay, and you can also have, and that's called deuterium. And if you have another neutron as well in the nucleus, that's called tritium. Now, on Earth, there's a specific ratio between light water, so the normal water, H2O, and the heavy water, which is D2O. And the ratio of these two um, molecules or these types of water gives us an idea of if the water has the same origins. And we discovered that what we found on Churi, the water on Churi, actually has 3 times more heavy water than the one that we have on Earth. So we understood that at least that comet and probably comets have not contributed to bringing water to the Earth and making it habitable. Now, the other thing that happened was that as we were developing this mission, we developed a camera because if you know comets and asteroids, they're very black. We developed a camera to look at the surface of the comet. And this camera is able to distinguish between very dark gray, black, light gray, so different shades of gray. And what this camera now is doing is that it's been installed over the tops of forests and looks at the treetops and sees whether there's an early forest fire detection that it can make. So it's able to distinguish between vapor, between fog, between clouds, and between a fire. And what you see here in the picture is one such detection that such a camera made some years ago. So this is, again, if you don't believe in the scientific enhancement and development and everything good that it does, we also do have some technology transfer that can be done for the immediate benefit. And I believe that Portugal being, unfortunately, that vulnerable to forest fires, such technology is certainly beneficial also to the country. As we were looking at Venus many, many years ago, we actually learned the whole topic of we discovered the whole topic of the greenhouse effect. So this is another example where looking at the solar system and doing scientific exploration has given us the tools, the data, the information to have an eureka moment and say, there's a greenhouse effect. Maybe this is what is happening on Earth. And that's actually how this whole thing started. Now the question, of course, is how will we tackle climate change, biodiversity, disappearance, and how space can contribute to that. Let me just go quickly through human exploration, and I realize that I really need to go faster in my presentation. On the International Space Station, we've done a lot of research, and we're still doing it, from new molecular biology to biotechnology to human physiology, to see again how we can understand better the human autonomy, to also bring benefit back on medical elements and research that we do back on Earth. We've also looked into material science because production of materials is actually different in vacuum because of all sorts of physical phenomena which are different. But a lot of what we do is certainly focused around human physiology. One interesting element, and this is not an ESA element, but was done at NASA, they took twins and they sent one twin to space and one stayed on Earth. And after the twin came back, they also compared if there had been changes. And what you see here is all sorts of things that they had looked into, comparing how the physiology of these two twins had been affected. One of the things that I found most interesting was the aging factor. And what they discovered is that the twin that was in space, to our chromosomes, there's a part at the end which shortens as we get older. And what was interesting to see was that the twin that was in orbit, these ends of the chromosomes, they became longer again. So somehow they discovered that, again, these ends of these chromosomes play a role in our aging process. Once the twin was back on Earth, they then realized that these ends of chromosomes was shrinking back again. So there's a significant number of research and there's a lot of the human body that we still don't know about, but these changes can help us, look into it. It provides us hint as to, what are the next questions that we have to ask and where we can start looking for answers. Another thing, of course, which is important for us when we send astronauts both to ISS, the International Space Station, or we want to send them to the moon or to Mars, is being able to take care of them from a medical point of view. So something that was developed or is being developed even more and more strongly is telemedicine. And telemedicine is certainly something which is important back on Earth. If you consider places of emergency where, for example, there's been a disaster and the infrastructure is broken, and you can go in with smaller tools and the doctor somewhere else. So telemedicine can certainly be of great help for us back on Earth. And for that, we also need to have so-called ubiquitous connectivity, meaning that we able to have, connection wherever we are. That's obviously another topic. If we think of Corona times today, where we're all sort of segregated and we can't be in contact with one another, certainly being able to do distant diagnostic of the human being that's not feeling well is certainly also helpful. Another thing that we do when we think about sending our astronauts somewhere else is closed life support systems, right? We have to be careful with how we manage waste and how we use resources, and we have to recycle elements as well. And if you go back again to the catalog that I was showing to you at the beginning of my talk, you'll see that there's also some elements that have come out of that. There is, for example, one small company that's looking into the ballast treatment of the waste on ships. Normally, the waste on ships is, if we're lucky, it's brought into port and then it's sort of disposed somehow. And what this company is doing is trying to take the knowledge that we've gained out of these sort of development of life support systems to treat the ballast water of ships so that when we reinsert it back into the environment, it's cleaner and it's less harmful. So it's again repurposing of used resources, recycling them, and again, it's contributing to a green environment. Another example that I love to bring is this one, where on the International Space Station, they discovered that plants have little enzymes in the roots, which enable them to grow their roots towards water. And the idea now here would be to take these enzymes and stimulate the growth of roots in plants so that they become drought resistant. So in places where there's less water, tackling again also the climate change that we have and making sure that there's perhaps no poverty, so because there's then food for all, we can have drought resistant plants. Now I'll go to the topic of safety and security. Here we see space safety and security applications, and cyber resilience. Space safety is about tackling challenges that come from in-space elements, so space weather, debris, and asteroids. Safety and security applications is about using space-based data to tackle safety and security issues on the ground. We have, for example, a charter which is called Space and Major Disasters, where we provide Earth observation telecommunication services for those areas that have been have undergone a major disaster like a tsunami and earthquake, to try and support the recovery, rescue elements, and telemedicine is also certainly something that can contribute. And cyber resilience is about, being resilient to both cyber attacks as well as things that can happen, which are just mishaps, right? As our society becomes more and more digitalized and more electronic, things can just go wrong. It doesn't necessarily have to be an attack. So we're also looking at those elements. You've certainly heard, if you haven't been lucky enough to see auroras, I understand that they're very beautiful. I haven't seen them myself, but these come from the sun. What the sun does is, other than bringing us warmth, it spews high energy particles at us. And the Earth has a magnetic field, which you see here in pink. And what these particles do is that they travel, and the solar wind travels at very high speeds towards us. It's deflected by a bow shock, which occurs because of, again, if you will, it's aerodynamic effects, but a bow shock around our magnetic field. But part of these particles are sort of sucked in at our magnetic poles, where the magnetic field lines, if you will, don't protect us anymore. And this is how auroras happen. As these high energy particles enter the atmosphere, you see this emission of light. Here's an image of the sun. You see these bright dots on the side. Those are actually the planets as they rotate around the sun. But here you see these coronal mass ejections, and these high energy particles, they do a lot of damage and disruption. Okay. Another thing that we need to know about the sun is that it actually goes through solar cycles. So we have just sort of come out of a solar cycle. If you look at here at the image at the bottom right, we have just finished one solar cycle and we're starting on another solar cycle. What the solar cycle means is that when you're at the bottom, the sun isn't very active, and when you're at the top, it's very active at, you know, with lots of sunspots, and it's spewing lots of high energy particles at us. What scientists do is they try and simulate the strength of a solar cycle, and what you see here is the simulations of the past and the prediction of the next solar cycle, which will be solar cycle 25, and experts say that it will be more or less the same as 24, maybe a little stronger. Another thing that I'd like you to know is that there is a motion of the magnetic field, if you hadn't heard of that before. And of course, this also plays a role, right? I was telling you that we are most vulnerable at our poles. So if the poles change, the places where we're also vulnerable also changes. Of course, there's also other impacts to the motion of our magnetic field, and you may have heard about swapping of magnetic field polarity, which would cause all sorts of other disruptions. But this for me is, you know, just about solar weather for the moment. At a solar minimum, again, when there's little activity, the sun looks, you know, like just a disk. And at a solar maximum, you will see that there's so-called sunspots. And the sunspots is where we have eruptions, but not only. Admittedly, we haven't understood much about the sun yet. One of the indications that we have that we're about to start is a new solar cycle is that the polarity of these sunspot swaps, it goes from plus minus to minus plus. And this is an indication that we have that something is cooking on the sun, if you will, right? So, and we're going to start a new solar cycle. Why is this important? It's not just important for exploration, right? If you look at this picture, you see that we're protected behind the blue sort of area. And if you leave that, so if you go to the moon, if you go to Mars, or even if you're at ISS, you're more exposed. But space weather has an impact on many other things as well, right? So we have increased radiation doses in aviation. We all use global navigation systems today because the interaction of these solar particles with the atmosphere causes changes in density of the atmosphere. It also disrupts or causes errors in satellite navigation. It can actually cause power surges in our power grids. And it's in the past, it actually has caused blackouts because of major solar events. Now, Portugal isn't in an area of high solar weather activity, but you know, if, for example, France is impacted and solar grids fail in France, there will be an impact on the power grid in Portugal because of consumption levels that will move around, or there will be more consumption than pulled out of Portugal. This is why we have to raise awareness of this topic and make sure that, again, non-space sectors know about the impact of space weather and we can prepare for it when it comes. Part of this preparation means doing some solar weather forecasting. So you all know about weather forecasting, that we, you know, look into our phones today, or the weather, what's the weather going to be like tomorrow? Well, one day I can tell you we'll be looking at that, and we'll be also wondering what the space weather is like. Indeed, we're now developing a satellite that will go to a so-called Lagrange point, 0.5. Without going into the details, this actually helps us look at the sun before it turns towards the Earth, and this allows us to have an early view of those sunspots that are developing on the solar surface. So we can do forecasting, but we also do nowcasting, right? So it's just like the normal weather, but it's solar weather. Debris. Indeed, sustainability of what we do is really important. What you see here is a picture of the evolution of debris over the years. Here you see the objects which are larger than a meter. Here you see the objects that are larger than 10 centimeters. Here you see objects that are larger than 1 centimeter. And these are the objects that are larger than 1 millimeter. It's a scary picture. I don't like it. And this is why we need to take we need to take care of it. It's not sustainable for sure. And I mentioned to you before the actual element of taking down objects, debris removal. But there's a whole topic of, again, manufacturing in space and recycling in space. And I don't know if the video will work in a second. There's companies around the world, and Portuguese companies are part of it, that are looking into manufacturing in space. And what you see here is a 3D printer, a high performance 3D printer that was developed to work in microgravity. So in a second, you'll see this 3D printer. Here it's horizontal. You'll see this turn, right? So it works in microgravity conditions. But what's also nice of this printer is that it uses recycled plastics. So it's not just it's starting to look at the circular economy. And my hope is that as we push for these topics in space, we also contribute to an awareness that in any case we have to have on Earth. These are some examples of the products that have been printed out of that printer. Okay, so I understand I don't have much time left, but I have quite a number of slides left, or things that I'd like to share with you, looking into the applications. Earth observation. We've developed lots of satellites in the past to look at the science aspects of our Earth system. How does our Earth work? How does climate interact with oceans, with water, with space? How does it interact with land cover and the biodiversity on this land cover? We've also developed satellites, again, for meteorology, for normal weather, and then we've developed together with the European Commission and the Union the so-called Copernicus missions, where we try and develop satellites that bring data that can also then be used for applications and downstream services. One of the things that I always like talking about is the essential climate variables. There's 50 so-called essential climate variables that are used to describe the climate and how it changes. Of these 50, 26 can be really only observed from space because of, if you will, the bird's eye perspective that space can bring you. And these are sea ice, sea level, sea surface temperature, cloud, greenhouse gases, et cetera, et cetera. So this is one contribution that we can bring. I mentioned the Aeolus spacecraft before, which measures 3D profiles of winds. This can certainly contribute to optimization of energies. When can we use wind turbines? When are they not helpful? Can we predict that? Predicting natural disasters. What you see here is a measurement from space of the elevation over a volcano, and that can actually help us predict if a volcano will erupt. So rather than doing support after it's happened, why can't we try and predict these disasters from happening so that we can save lives, save infrastructure? Plastics is another element that we're looking at. Portugal Space has been very active in this with a moonshot activity, which has challenged Earth observation or space people to come together with artificial intelligence experts to try and see whether we can use space-based data to identify, monitor, and track plastics on the ocean so that we can deal with this topic and clean up our oceans. I mentioned telecommunications. Of course, many of these elements need that we are able to communicate, right? So having so-called ubiquitous connectivity. And one of the things that we do is we try and put assets in space so that we can connect across the globe with a sort of ultra high-speed optical network. And what's also interesting for us is to make sure that this optical network doesn't just allow us to communicate from one side of the Earth very rapidly because the satellites have, less to travel and they don't have to go through the atmosphere. So they have less nodes also to go through, but to make sure that these connections are also secure. So using the element of quantum entanglement, we look into cryptography to make sure that the information can be transferred from one part of the planet to the next in a secure manner. I like to show this picture, which shows Portugal mainland very well connected, and then we see that the Azores are connected through undersea cables. And the Atlantic being so important for Portugal, having resilient connectivity is important for all sorts of elements if we want to be active in the Atlantic. So having, in addition to that cable satellite connection, allows us not only to make sure that we have an infrastructure in the Azores providing communication, but that ships in the Atlantic and anyone else in the Atlantic that's doing either business or, you know, providing for safety and security for defense purposes actually has communication means, without which operations are impossible. Satellite navigation. Satellite navigation actually comes from the special theory of relativity, according to which, you know, if we are, we have, according to which time is impacted by speed and gravity. And as it says here, time is slowed down due to speed. And this was given by the general theory of relativity of Einstein in 1915. But we also know that time is slowed down due to gravity. Now, these two elements do not cancel each other out. And this has actually been extremely important for us to develop navigation systems that are actually accurate and that you can use and I can use in my mobile phones on a daily basis. Without this knowledge, the navigational errors that we would have would be 500 meters in an hour. We use Galileo, which is the European Global Navigation Space System. So don't use GPS anymore. It's not as good as Galileo. Galileo is a lot more accurate. We use Galileo and an enhancement system, which is EGNOS, to do all sorts of things, like, for example, land planes in airports and to navigate planes around urban regions in such a precise way that we can avoid, for example, excessive noise disturbances for populated regions. So, and by the way, there is an app, I think it's called GNSS System, which shows you which GNSS satellites you currently have overhead and you can use if you obviously have the right tools for it. And currently, if you have the latest mobile phones, you will have those certainly available. Now, Portugal is very interested, like other countries, to make sure that all of these benefits are, you know, brought really to the economy and to society. And how we do that is that we also have business incubation centers where small startups can develop ideas based around products which they think are important. And just earlier this year, through Portugal Space, the ESA Business Incubation Center was enhanced from 3 to 15 centers. Why am I mentioning this? This is actually very important because it means that space is going to the regions, and these regions and the people in these regions can address their challenges by, again, going to these business incubation centers, receiving the benefit of accessing space-based data and being sort of incubated, but they're not, they again, they can address the challenges of the regions that they're located in. So it's about bringing space across to the entire country of Portugal. This is one example of you know, some of the elements that are done in the downstream. For example, and I'm sorry that the text is a bit overriding each other, trying to see whether transmission lines, power lines, are cleared of trees. And this, as you know, is one of the causes why we have sometimes forest fires that develop in Portugal. We are able very easily from space to see whether this is the case. So there have been companies, and it's been developed by GMV in Portugal, that have looked at developing a service by which we can really see whether, when it comes to that difficult period during the year, the transmission lines are clear, and if not, that they be cleared. One of the other things that we've done, and this was during COVID, was to do some rapid action. And the idea here was, and do please visit the website, it's race.esa@int, to develop all sorts of indicators to see how the current crisis has impacted society and economy at large. And through that, you know, we've been able also to, again, develop additional downstream services and applications that have benefited the economy, or again, people across the different countries. I have a couple of examples. I'm very wary of the time, so I'll try and you know, go through very quickly. Here is one example for Portugal, where based on data from Tropomi, which is an instrument aboard the Copernicus Sentinel 5P satellite. You can see how the air quality in Lisbon has developed over the months and over COVID. You see on the left-hand side all sorts of available indicators that were developed during time. What you see here is another one. This is not related to Portugal. Unfortunately, I couldn't find an example for Portugal. But what you see here is that various parts of Spain, the actual harvesting was monitored over the months to see whether there had been an impact during COVID. As you know, workers and sort of workers, not permanent workers, had a difficult time moving from field to field or from place to place during COVID. So there was an examination of whether the harvests had been as successful as in the past. What you see here is, for example, the water quality in Venice. You've may heard in the past that Venice water quality is not always good. And this was another indicator that was developed to see whether during the COVID time, the actual water quality was better. What they discovered here is that the water quality was better, but there had been also a shift in the temperature of the water. And therefore, they couldn't really decouple and say whether it was just COVID or not. Another indicator which I found quite interesting and which hits my home country is Italy. And this was just to see whether during COVID and because of, some of the collapses in the systems that normally served us and, served daily life, like waste management, if there had been an impact. And what you see here is that they indeed detected that there had been an increase in stored wastes because the systems had not been able to keep up the processing volumes that they had in the past. So these are all sorts of indicators and elements that were sustained and supported by imaging that was done from space and then analyzing, and this is extremely important, analyzing this data together with other terrestrial information that was gathered. Before I sort of conclude, I just wanted to say and bring another example, which is close perhaps to Portugal. If we look at the sustainability and we look at the use that Portugal could make, for example, of the Atlantic, one thing that we could think of is aquacultures. And, I'm sure you've heard of this element for sure. If we want to use aquacultures and exploit the ocean and the Atlantic to the benefit of the economy and society, then obviously we need to make sure that the production that is done is sustainable and is optimized. And one of the ways of doing it is by making sure that the aquacultures are placed in good regions where the temperature is good. And having that information from satellites in low Earth orbit, as I was showing to you before, is information that can benefit these aquacultures. Now, if you imagine that during the year, the temperature of the water varies, then you can easily think that during the year, these aquacultures should move from place to place. And that's also what, fishers do. So imagine a future in which we have aquacultures that autonomously move from one location to the next using Earth observation information and Galileo information, so positioning and timing information. And we will have developed a new economy around sustainable food production. We know that fish is the more sustainable food source than, for example, meat. Although, of course, we need to make sure that we don't fish out more than than we have in the oceans. But that's one way also Portugal could bring a huge contribution. Now, finally, just last picture, and then I'm done. We are very interested in working with artificial intelligence and with big data, right? It's not about space doing something in isolation. I've tried to show to you how we're really keen on bringing space sector close to other sectors. And one of the things we want to do is develop, for example, a digital twin Earth, where Earth observation information, telecommunication information, navigation information, all of this information that we gather from space and through space activities comes together so that we have a model of understanding of how our Earth system works. But further, we understand how economic sectors are dependent from one another, and we can have better decision making, and we can have governments in also hard times such as COVID being able to, bring populations forward in a positive way. I'm always, in favor of positive rather than destructive messages, where we can have positive decision making by our governments and bring forward again society and economy in the best possible manner. So again, space for you and space for the benefit of all of humanity, as in the Portugal space vision. So with that, I finish, and as Spock would say, live long and prosper, especially in these very difficult times. Thank you very much for listening, and I hope I didn't do too much in terms of going over the time. I'm sorry for that, Joanna. I hope it's not a problem.
Not at all, Chiara. Thank you so much for your interesting talk. I think we have no more questions, except someone is asking the name of the website on the chat when you were speaking about the COVID tackle and how you were looking into that.
Okay, I'll write it. I'll write it in the chat in a second.
Okay, and can you give us some examples? For instance, how does space exploration contributes for fighting hunger or other society problems?
As I mentioned, Joanna, one of the examples that I find the most interesting is this development of plants which can be drought resistant, right? But there's lots of research that goes on because, of course, if we think of exploring further, we have to sort of be able to produce these elements and be sustainable in a very closed environment. So it's all about using resources that we have at our disposition in a very economic way, right? So again, for example, developing these drought-resistant plants, reusing wastewater. I mean, it's no secret astronauts do end up drinking their own urine, but it's it's recycled, right? And they don't. It doesn't take. It's purified water, and all of these elements contribute to a more sustainable society on Earth. We are a consumer society today, so we don't always, or we haven't in the past, looked at things from minimizing the resources that we use, but in space we are forced to. So all of the technologies we develop are in that sense, and these we always try to spin down back to Earth. It doesn't always happen that quickly because there isn't necessarily a need. Something which is recycled at the beginning tends to be more expensive that something isn't. But the technologies are there and we try to spin them back.
Okay, like for instance, the United Nations World Food Program uses the satellites to see where refugees groups are, and then can really intervene in a precise region, for instance.
Yeah, that's an Earth observation, right? So we can take pictures and see how in which places we need to intervene and do rescue and humanitarian support. Yes, without a doubt. With Earth observation and again communication, because generally remote areas do not have any communication means. So if you don't have, even if you have a mobile phone, but there's no terrestrial infrastructure, you won't have a connection. So we need satellite communication, and then we have sort of mobile terrestrial receivers that can help us. I've posted the website, by the way. It's called race.esa.int again, and the SDG website as well is quite interesting, and that's the same. It's sdg.esa.int. But if people Google, it's very easy to find as well.
Okay. So we don't have further questions. Thank you so much, Chiara. It was very interesting to realize how much ESA is contributing to our daily lives, actually, and to preserving all this environmental, and with this recycling also that most of us don't know, that actually there is really concerned not to pollute anymore. We usually think, that the space is overpopulated with satellites and that it's contributing to pollute the Earth, but actually it's the other way around.
we try to do our best, but I know we can do more, right? Funnily enough, we had a questionnaire that we asked to citizens that are not, in the space sector, and we asked them 2 years ago, no, a year and a half ago, how much a general citizen would be happy to contribute to space because of the fact that space brings so many benefits, and the average citizen said 253 euro per citizen per year. And actually, we are only spending 8 euro per citizen per year, and in Portugal, it's even just 2. So it's, yeah, with that money, we're actually doing quite a lot.
Okay, thank you so much, and hope to have another talk soon.
Thank you, Joanna, for having me, and it was a great pleasure to be able to share all of this with you. So
Okay.
I wish you all the best, and yeah, take care, keep safe, and again, live long and prosper.